The CARMEN tool features advanced capabilities for detecting and analyzing industrial traffic, being able to process, dissect, and examine protocols such as DNP3, ICCP, and MQTT.
In this demonstration, we show how CARMEN is capable of detecting a rogue master attack TO-848 MITRE attacks ICS. This technique consists of an attacker setting up an unauthorized fake master or broker to which devices may connect. In this way, the attacker can send fraudulent commands and publications that put the network at risk. For the test, we injected into CARMEN a PCAP file with real MQTT traffic. Thanks to the MQTT dissector, developed under the R²D² project, the tool can apply Deep Packet Inspection, DPI, analyzing each packet in detail and displaying protocol-specific fields such as commands, records, IP addresses, and ports. First, we show the information contained in the PCAP using Wireshark, where the traffic already appears dissected. It can be observed how the broker uses the source IP with the standard MQTT port 1883 communicating with the destination IP on port 49420. These same IPs are repeated throughout the PCAP file, since in this demonstration we only have one broker and one subscriber.
Next, we visualize this same injected and dissected traffic in the CARMEN tool itself for the MQTT protocol. The interface allows us to apply filters more easily and check the information. We verify that the tool shows exactly the same source and destination IPs we had previously seen with Wireshark. We then run the anomaly analyzer, designed to detect technique T0848. This analyzer maintains a dynamic dictionary, or baseline, that automatically learns from all legitimate IPs and communication combinations. When a new IP, an unregistered connection, or a suspicious broker appears, the analyzer automatically generates an alert with an anomaly code and an associated score, indicating the level of detected risk, since it could be a rogue master attempting to connect with other subscribers. While results are being generated, we review the accumulated detections from previous runs of the same day. On some occasions, the analyzer has registered up to 181 different connections. We analyze in detail the last detection recorded at 1304, where the analyzer identified a new unknown connection between two IPs. This was marked with an anomaly score of 100%, since it had not been previously seen in the baseline. We return to the general list of analyzer results and confirm that the execution we just launched has already finished. In this case, no new anomalies appear because those connections had already been recorded in the tool's dictionary. To validate correct operation, we load a new PCAP that contains unknown IP addresses not registered by the system, attempting to establish communication with the client. We return to the CARMEN tool and rerun the same analyzer, extending the observation time range. In the results, we can see how the analyzer detects the presence of a new IP attempting to connect with a client, which had not previously been mapped in the analyzer's baseline. CARMEN immediately flags it as a new anomaly, generating the corresponding alert. This experiment validates that CARMEN is capable of detecting the rogue master technique T0848 in MQTT traffic, identifying the presence of fake brokers and strengthening the security of industrial networks against initial access attacks. S2TH is an AI tool developed within the R²D² project to improve the accuracy and effectiveness of APT detection by CARMEN. It takes as input both historical APT threat intelligence and the standardized results of CARMEN's analyzers. By correlating these two sources, the system can detect possible traces of APT activity.
The baseline intelligence covers IT and OT attack techniques used by different APT groups, normalized using the MITRE attack framework. With natural language processing, each tactic and technique in the database is projected into an n-dimensional space. The same process is applied to the results from CARMEN's analyzers. By placing both datasets in a common space, We can measure their distances and relationships. In this first example, the input projection, star symbol, is not close to any APT activity, so no alert is generated. In the second example, the projection matches an APT technique, triggering an alert. Here, the similarities between the input and the APT group using similar command lines are clear. In practice, S2 is already trained within CARMEN using APT intelligence models, so its task is to look for new matches. Here we show part of this intelligence as a reference.
CARMEN's IT and OT analyzers examine network traffic and generate results periodically. Like the example shown here with multiple findings. S2 checks these results every few hours to identify alerts that may be linked to signs of APT activity.
With requests like this to our endpoint, you can verify the outcome. When a match is found, it is stored in a local file, like the ones displayed here. This helps to analyze the outcome and review similarities. In the next stage, these results are consumed by ADR, the following module in our workflow. S2 has been responsible for linking the results of the CARMEN analyzers with APT groups and has generated related alerts in the tool. These alerts are analyzed by the ADR module, which calculates the probability of an APT group encountering a specific asset within the organization.
The module uses a CSV asset map to identify possible attack paths to key assets. Another CSV marks internet-exposed entry points and defines which assets are critical targets.
What the ADR module does is take all the possible paths between the initial access and the key asset and calculate the probabilities that different APT groups, using certain techniques, will be found in each of the assets, as well as the final probability that that group will reach the target node. These probabilities may vary depending on the alerts received. When CARMEN receives an alert, the probability that that particular group is at the node where the alert was triggered automatically becomes 1. From there, all options are recalculated. As we can see, we have a graph with the organization's assets.
IP address 10.2.124.3.50 corresponds to an initial access asset, while the IP address 10.222.142.1 corresponds to the key asset to be reached.
We can see how, from the initial access to the key terrain, the attacker can take 3 different paths, depending on which they will encounter more or fewer assets.
When the attack began, CARMEN had generated an alert associated with the APT29 group when the attacker accessed asset 10.10.50.11 from that moment on. The ADR recalculates the probability of the adversary reaching the critical asset. Since there is only one path to the key asset from that point, all probabilities become 1, as there are no other access alternatives. Let's test this hypothesis with the ADR module, which has 3 API calls to query this information. We launch the first query to get _full to obtain all the probabilities associated with the asset map. After execution, many results are generated and stored in an output file. The first part shows the nodes, with information related to specific IPs, the layer they are in, and the type of asset, whether it is an approach asset next to key terrain, whether it is key terrain, etc. Next, the relationships are shown where the specific APT group can be seen, along with the probabilities that this group in that node will use the collection technique or input capture. For example, at IP 10.224.3.50, the calculated probability is 0.0334. Given that an alert associated with APT29 had already been generated in CARMEN, the ADR module interprets that, from that point on, all scores for APT29 should have a value of 1, as the alert confirms the actual presence of an ongoing attack. The get_probability query is also available, to which a specific IP is passed to obtain information only from that asset. In this case, the IP address 10.222.142.1, corresponding to the key asset, is queried. When reviewing the result of this query, we see that it only includes information about probabilities, showing exactly the same information as before, but filtered only for relationships where the specified IP address appears. Finally, there is the get_actors call, which also receives a specific IP address and returns the APT groups that can attack that particular node. The information for IP 10.222.142.1 is queried again, and the result shows that one of the actors that can affect this key asset is APT29. This is precisely the one that generated the alert in CARMEN, showing that it had a 1 in 1 chance of reaching the key asset. If alerts had been generated in other nodes, or if alerts from other APT groups appeared in this same node, these would also be reflected in this query. The ADR module has thus demonstrated that the hypothesis based on the alert generated in CARMEN was correct.